Okay, so that's the properties of water, and again, they can all be traced to those polar covalent bonds leading to hydrogen bonding between molecules. So now we're going to talk about solutions, solutes, and solvents and how they relate to one another. So here are some definitions for you. A solution is a uniform mix of two or more substances. A solvent is the liquid phase of that solution, the liquid that dissolves a reagent or a chemical in the solution. The solute is the dissolved reagent or the chemical that is dissolved in the solution. So a solution is solvent plus solutes. And water is a very, very, very good solvent. And again, this is something that can be traced to hydrogen bonding. So we talked about ionic bonds in the last chapter, earlier in this chapter, and I told you that ionic bonds can be very strong, but it depends a lot on the environment. So salt that's in a salt shaker that's kept dry is a very recalcitrant material. It doesn't just break down spontaneously. But then you add salt to water and it dissolves almost instantly. And the reason for that is because those ions start to come apart in the water. And the water molecules start to become attracted to those ions. Only different parts of the molecules are attracted to different types of ions. So the negative end, the partial negative ends of water molecules are attracted to the positive charges on the sodium ions, as you can see up here. And the partial positive charges on the hydrogens are attracted to the negative charges on the chloride ions. And so they make these barriers that keep those ions from interacting again. And we call that a hydration shell. So this chloride ion has a hydration shell of water molecules that are all pointing their positive charges, their partial positive charges. And the same thing's happening with the sodium ion, that it's got all of these oxygen ends, the partial negative charges. So these two don't interact anymore once they dissolve in water. And it isn't just ionic compounds. Any compound that is polar, that has partial positive and negative charges on it, even if it's a great big molecule, like a great big protein molecule that's hundreds or thousands of Daltons, you can dissolve it in water because this purple blob in here represents a great big molecule that is dissolved in the water because there's a hydration shell around it. So even though it's big and complex and it's got partial positive and negative charges all over it, water is still going to form a hydration shell and prevent this giant purple molecule from interacting with any other giant purple molecules in solution. So this type of thing only happens with polar and ionic compounds, which is a lot of compounds. So substances that dissolve in water or are attracted to water, we say, are hydrophilic, which means water-loving. But substances that are nonpolar, because the atoms are sharing electrons more evenly, they tend to repel water, and we see that they're hydrophobic. So substances that are nonpolar and non-ionic are hydrophobic. Like, you've probably seen this if you've ever had a salad with a simple vinegar and oil salad dressing. Vinegar is very watery, oil is not, and if you have to shake it up before you put it on your salad because the oil and the water, they don't mix, because the oil is hydrophobic for reasons we'll get into later, and the vinegar is very watery. Okay, so this slide looks like it's very complicated, but it's we'll take it slow. So the amounts of reagents are important, right? So as an example, if you were going to make a cake, unless you've spent a lot of time cooking, you're probably not just going to guess how much of each ingredient you're going to put into your batter, right? because that's a bad idea. You're not just going to be like, well, let's see, how about 3 cups of salt and a tablespoon of flour and 15 eggs and a drop of water. That would make just a terrible cake. You don't have to test this hypothesis. Just believe me, that would be a terrible cake. So in order to have a recipe where you have a cake that comes out really good, just like the one that you see on TV, you need to fix ratios. You need to put the same number of eggs as Wolfgang Puck puts in his cake, or some famous chef. You need to put the same number of cups of flour, or teaspoons of salt, or baking powder, or whatever it is. If you want your cake to show up and be just like his, you've got to follow the recipe. So that's something that we want to do in our own bodies. And if we want to make up chemical solutions, we want to do the same thing. So we want to calculate molecular weight. Now, molecular weight is the sum of all of the atomic weights for a particular compound. Okay, so sucrose is the scientific name for table sugar. So if you put sugar in your coffee, what you're putting in is a compound that is 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. So 1 molecule of sucrose weighs whatever carbon weighs times 12 plus whatever hydrogen weighs times 22 plus whatever oxygen weighs times 11. And rather than go through a bunch of mathing it out, I'll tell you that is 342 Daltons per molecule, or atomic mass units per molecule. Okay, but Daltons are a very, 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 very small amount of mass. We don't have a scale that can measure a number that small. It can't measure 1 molecule of sucrose. We live in a macroscopic world, so we want to have some way of having a consistent amount of sucrose whenever we want to make a cake, for example, or make a sucrose solution, add sucrose to water in a lab for an experiment. So the way that we do that is we have a conversion factor. And that conversion factor is called Avogadro's number. And Avogadro's number is roughly 6 times 10 to the 23rd power. So what that means is that 6 times 10 with 23 zeros after it. So this is what we call scientific notation. And in scientific notation, the number of zeros is very important. So a 1 million is 1 with 6 zeros after it. So that's 10 to the 6th power. 1 billion is 10 to the 9th, or 1,000 times a million. So 10 to the 9th. A trillion is 10 to the 12th, which is 1,000 times a billion, which is 10 to the 12th. So 10 to the 23rd, that's practically a trillion molecules, or atomic mass units, in 1 gram. And we call that number, this 6.02 times 10 to the 23rd, a mole. And basically all that number does is it's kind of a way of saying, alakazam, we started with Daltons and now we have grams. So that we know that if we weigh out 342 grams of sucrose, that we've got this many molecules. So we know exactly how many molecules there are. So what happens if you cut an avocado into 6 times 10 to the 23rd pieces? Guacamole. Okay, so we use moles to fix ratios of molecules. So if we want to add 1 mole of sucrose to 1 liter of water, we would call that a 1 molar solution. And if someone walked into the lab and said, this is, oh, here, look, here's some 1 molar sucrose, they would be able to say, oh, there's 342 grams of sucrose in this liter of water. So the molarity is the number of moles of solute per liter. So this is getting kind of deep and sciencey, and hopefully you're still with me. But this is going to be very important for us to figure out how acids and bases are defined, and how do H plus and OH ions determine pH, and why is it important to living organisms.